Greetings everyone, and welcome to section 5.1. In this section we look at continuous random variables. So I've already written down some notes. You'll recall that for discrete random variables, well, first of all, a random variable is the result of a random or chance event, and a discrete random variable you can only take on certain values. So for example, if you are rolling a die or a few die, then either the individual rolls or the sum of those rolls or even the average of those rolls can only take on certain values. And today we're going to look at the idea of continuous random variables, where you can take on an infinite number of values and, at least in theory, can always split the difference between any two values. So let's write an example. If your variable is time, and you have measured the values 2.78 seconds and 2.79 seconds, you could, in theory, also measure a value of 2.785 seconds. So you're splitting the difference. Now, this runs up against real life in that our clocks are only so good. Even if you have an atomic clock, there is a limit to the amount of precision that you can measure. But in theory, could you measure halfway between two instances? Yes. So what does a probability distribution look like if you've now got an infinite number of values? Let's just write down that sentence. So what does a probability distribution look like if you have an infinite number of values that your variable could take? So clearly you've got a little bit of a problem in that normally, remember what a probability distribution is. It is a formula, graph, or a table that lists all of the possible values of x and the probability of getting each of those values. But if you've got an infinite number of values that x can take on, then clearly you can't just list all of them. And also, we have a bit of a probability issue in that if you've got an infinite number of values, what's the probability of getting any one of those values? It's going to be 1 divided by the number of values, which is infinity. And, well, that's kind of more of a calculus idea, but you can see we've got a bit of a problem. We're going to sort of skip around it a little bit. What you could do, you could group the data into bins and make a histogram. So, for example, if you're taking times and your time is anywhere from 0 to, oh, I don't know, 3 or 5 seconds or something like that, then you could actually group all your data and put all of the instances in which you've measured a time between 0 and 1 seconds in the first group, and between 1 and 2 in the second, and between 2 and the 3 in the third, and all the rest of it. And then you can make a little probability distribution that I'm just making some stuff up here. Looks, for example, like this, where this is the time in seconds on the x-axis, this is the probability on the y-axis. And then, for example, this bin contains all events with time between 3 and 4 seconds. And then, of course, once you've done that, then you can make sure that all of the probabilities sum up to 1, just like we did before, and then you're okay. But let's suppose that you didn't want to divide things up into just only 4 groups. You could do the thing where instead of grouping it from 0 to 1, and 1 to 2, and 2 to 3, and 3 to 4, like before, where this is the time in seconds. This is probability, so you could take the number of instances and then divide by the total number of measurements that you made. But instead of doing just such really large bins, you could split them up into smaller bins. Let's say our numbers only go up to 4, for example, and then you might get something that looks like this, and then that, and then a really big guy. And you can sort of, I'm just making this up, but you can see how you could get a distribution that looks more like this. So smaller bins. Where all of your probabilities are still adding up to 1. Or you can probably see where I'm going here. You could do the thing where from 0 to 1 you've got a whole bunch of tiny little bins, etc., etc. So you got tiny little bins. I'm not even going to bother to draw this out, but you get the idea. Apparently I can't spell tiny. And for those of you who've taken a little calculus, you can probably see where this is going. You take the limit of you take the limit as your bin size goes to 0, but for everybody else, we're just going to say that eventually the rectangles will get so small that you can't even see them. And you will get a smooth, continuous curve. And then your curve might look something like this. This is time in seconds, and we're going to leave the y-axis unlabeled for a second. This smooth curve is called a density curve, or sometimes it's called a probability density curve. Now, the thing about it is that it's a nice smooth curve, so it with an infinite number of points on it, so you can't just add up all the probabilities for each of those areas. So we're going to do a different thing, and we're going to look at some properties of density curves. Number 1, it is always on or above the x-axis. In other words, the y value is never negative. And number 2, the y-axis isn't probability anymore. Rather, the scale on the y-axis is chosen such that the area underneath the curve is exactly equal to 1. If you prefer percentages, you can think of that as 100%. So let's just go up to our picture again. We can see here that our y values are always either on the x-axis or above. We're never going to dip below it. We're not going to worry about what the y-axis is called anymore. Rather, what we're interested in is the area underneath. So if I were to take my little highlighter pen and highlight this, basically this area is equal to 100%. Now, you could say this one seems to go on for quite a while, but if it tails off and hits the x-axis eventually, then you can consider that the total area under the curve is going to be a finite or bounded quantity. And we're just not going to worry about it, even if it's going all the way to infinity, but just really getting really close to x. Those are some calculus ideas, which we're not going to go into. But basically, a density curve is some graph in which we're looking at the area under the curve instead of adding up the probabilities of the individual points.